All right, the natural logarithm. So they remind you here of your general power rule. We are going to be using that, but the thing about the general power rule is it works for antiderivatives as long as it's not a -1. So if I were to say x to the -1, what would happen here? Well, I would end up dividing by -1 plus 1, which is a problem, right? And so the general power rule works for everything except really x to the -1. If I have x to the -1 and I add 1, I would zero it out, and then I would divide by my new exponent, which would be 0. So then that is a problem. And so this is where we start looking at natural logs. And so if you look right below that, you will see how the natural log function helps us here. The natural log of x is defined this way. It equals the integration from 1 to x of 1 over t dt. What does that mean? Well, it means that the antiderivative of something to the -1 power is the natural log of that thing, okay? And so if I have 1 over x and I need to take the antiderivative, I cannot use the power rule because that causes a problem. What I can use is the definition of natural log. So if I am trying to do this right here, that is the same thing as this, right? If I were to try to use the power rule, the rule says add 1. Well, -1 plus 1 is 0, and then divide by your new exponent. That is the problem, okay? And so this does not work. We define our natural log by that antiderivative. The antiderivative of this would just be the natural log of x. And then, of course, it is plus c because we don't have an upper and lower bound there. So that's what that definition tells us. If I have 1 over x and I'm taking the antiderivative, it will be the natural log of that x, okay? So that's what we're introducing in this particular chapter. Let's talk about just natural logs. So for right now, these first few things are just talking about natural logs, and they're going to look very, very familiar. All right, the first thing is just the properties of natural logs. The domain is 0 to infinity. The range is all real numbers, pretty much. Negative infinity, positive infinity. It's continuous increasing 1 to 1. It is concave down. And they give you a image of what a natural log looks like. Because if you were to try to put in your calculator the log of a negative number, it's going to say, no, that doesn't work. Because if you'll recall, the reason this first property exists is if you will recall, like if I were to take the natural log of, let's say, 10, I'm saying e to what power equals 10. You can do that. It's going to be a decimal. E is what, 2.17, and so on and so forth, non-terminating, non-repeating decimal. You can do that. You can take e to some power and get 10. You can actually take e to a power and get something smaller than e. So if I wanted to say the natural log of 2, all right, that's fine. But the problem comes in if I were to say e to what power equals -4. Well, I can't take a positive number to a power and get a negative number. So that's why this is here. It's always your natural log, that has always been its domain, okay? It has always been positive real numbers, all right? So these are normal, and we've seen these before. The next set we have seen before as well. Properties. The log of 1. Log of 1 to any base, whether it is natural log or any other base, is going to be 0. E to what power equals 1? Well, e to 0. Remember, any number to the 0 power equals 1. So we already know that property. If these are the expansion properties, if I multiply two numbers within a log, I can expand with addition. If I have a power in a log, I can pull it out in front. And if I divide within a log, I can expand with subtraction. That should be very, very, very familiar. All right, we did this in Algebra 2. We did this in Pre-Cal. Okay, and so you can expand and condense with these properties. And we are going to use expansion and condensing to do derivatives, to make our derivatives easier. Let's look at just basic expanding and condensing. All right, so if you turn to page 316, you will see basic expanding and condensing. I'm expanding division. Well, I'm expanding that with subtraction. This is to a power. So if I were to do b here, I would rewrite it like this. And I can expand by pulling that in front. Remember, too, it'll often be written like this. You'll see it that way as well. If I'm expanding this one, I'm going to expand with subtraction, and then I'm going to continue expanding this guy with addition. Right? And you can do it as large as possible. So I can expand this one, this last one. It's going to be a little bit bigger, so we'll make some room. We can expand with division first. Minus this guy. Then I can expand each one of these, pull the 2 in front. Expand this with addition here. When I do this, by the way, you do need to bracket that when your addition is behind a subtraction because those are both being subtracted. This is going to be important when you do derivatives, so just remember your rules here. And then you can, if they do distribute that negative, you can distribute that negative as well. So this should be familiar. Expanding and condensing should be very, very familiar, hopefully. So let's try a couple. The first one is not intuitive necessarily. So you need to think about how you can rewrite 24 and then use the information that they gave you to expand and use those numbers. 20 and 30 are expanding and condensing. So try those 3. Natural log of E. That can be defined this way. It equals 1. Anytime you take a natural log of base to a base or a log base of the base, it's going to be 1. So if I were to do it with a different base, it's going to be the same. Log base 3 of 3 equals 1. The base of natural log is E. So anytime you take a base of a base, you're going to get that 1. Evaluating natural logs. We're not going to spend a lot of time here. Honestly, you're not going to do a lot of estimating of this. You're going to use a calculator to do a natural log. Like it is an irrational number. You can estimate them like we did if we knew some more information about it, but really for the most part, you will be using your calculator to do natural logs. So how does this affect derivatives? Let's look at the derivatives of natural logs then. So we defined it at the beginning that the antiderivative of 1 over x is the natural log of x. So it makes sense then that the derivative of the natural log is 1 over x. So if I have the natural log of x and I'm taking the derivative, that's always going to be 1 over x. What happens when I have a function inside of there? That u represents a function, let's say x squared. That is going to be the derivative of the function over the original function, okay? And we're going to do some of these so you can see what it looks like. But natural log is always going to be 1 over x. Natural log of some function is going to be the derivative of the function over the function. And very often it will reduce depending on what type of function you have. Let's look at these examples here. Example 3. d dx, that's just saying find the derivative. Find the derivative of the natural log. What's inside of my natural log? 2x. So on top, I am going to take the derivative of 2x. What is the derivative of 2x? 2. And on the bottom, I'm going to have my function that was in there, 2x. That reduces. What does that reduce to? 1 over x. That is my derivative. All right, let's look at the next one. Inside the natural log, I have x squared plus 1. What's my derivative? 2x. That's my numerator. My denominator is what was inside. All right, easy enough. All right, let's look at this next one. All right. This one is going to be the product rule. All right. Think of it as x times the natural log of x. All right. X times the natural log of x. So I'm going to say the derivative of the first. What is the derivative of x? Just 1. So I have 1 times my second equation or function there, ln of x. Then I add to it the first one, x, times the derivative of the second one. What's the derivative of ln of x? 1 over x, right? And so I end up just getting the natural log of x plus 1. That is my derivative, all right? This last one is the chain rule, okay? So the chain rule says, take this and multiply it in front. So I have 3 natural log of x squared, and then I multiply that by the derivative of the inside, which is just 1 over x. And so you can, if you want to, 3 ln of x squared over x. You can't really reduce that. You can't reduce inside the log, outside the log. So those x's do not reduce. You're pretty much done. All right, for this one, I am actually going to use my properties of exponents before I do my derivative, because inside the derivative, inside the natural log, I would have a chain rule type thing going on. So as opposed to trying to do derivative of the inside over the inside, we're actually going to expand it. We're going to use our properties here. So I can actually rewrite this like this, which is the same thing as 1/2 the natural log of x plus 1. And now I can take a pretty easy derivative, right? My derivative here, the 1/2 is just going to multiply. So 1/2 derivative of the inside, well, that's just 1 over the inside, x plus 1. So I end up with just 1 over 2 x plus 1. Much easier than trying to do the derivative of that chain rule, where you would end up with negative exponents and then have to simplify it out, okay? So expanding it helps. Expanding it before I take the derivative helps me do that. So let's do a couple of those. So normally this, if you saw this derivative, you would be like, what? I don't have any desire, right? But we're just going to expand it before we do. And then we're going to have multiple natural logs that we're going to take the derivative of. So I'm going to use my expansion rule. So this is multiplication. So I'll say the natural log of x. And then, of course, I'm going to say plus. This has an exponent. So 2 times the natural log of x squared plus 1. And then that division does a minus. That has an exponent of 1/2. The natural log of 2x cubed minus 1. All right, expand it. And then I'm just doing individual. When I take derivatives, remember with addition and subtractions, you can do them individually. And so I am going to do the derivative of each one of these individually, right? The derivative of natural log of x is just 1 over x. This derivative is 2 times the derivative of the inside, which is 2x, all over the inside. And this is 1/2 times the derivative of the inside, all over the inside. And then I'm going to simplify it. So the first one doesn't simplify. The second one, 2 times 2x is just 4x over x squared plus 1. And then this can simplify here, so I end up with minus 3x squared over 2x cubed minus 1. So if I were to take this derivative prior to this, you would do the quotient rule. And you would do a really nice, large, ginormous quotient rule that includes the chain rule is what you would do, okay? So instead of doing that, we are actually going to use our natural log to help us make this our life just a little bit easier here. So what we're going to do is we're going to take this guy and we are actually going to multiply both sides, or not multiply, but take the natural log of both sides. All right. So I am going to take this and I am going to do natural log of both sides. Whatever you do to one side, you can do to the other. So this is what we're going to do here. We're going to do the natural log of both sides. We're going to expand that right side like we did in that other problem. So we're going to say the natural log of y equals to natural log of x minus 2 minus 1/2 natural log of x squared plus 1. And now we're going to take the derivative of both sides, okay? So the derivative of the left-hand side is the derivative of the inside, which is what we're actually looking for. We're looking for y prime over what was in there. So we are going to have to go back and get rid of that y at the very end, but we'll do it at the end. And then on the other side, we're just going to take our derivatives. So 2 times the inside derivative, that's just 2 times 1 over x minus 2. This is going to be 1/2 times, so if I did this 1/2, this would be 2x squared on top over x squared plus 1. So my 2's are going to cancel. So I have x squared over x squared plus 1. All right. I'm trying to find y prime is what I'm trying to find, right? So on that left-hand side, to find y prime, I need to multiply both sides by y. So multiply by y, that gets rid of it there. But if I multiply by y on the other side, I now have like multiple variables. So I'm actually going to multiply by what y equals. All right. So I'm actually going to multiply this guy by y. But in doing that, I'm going to multiply it by what y is. And y is x minus 2 squared over the square root of x squared plus 1.
How do you get x squared on the right side?
This right here, that shouldn't be there. That's just 2x. That right there. I wrote it wrong. There we go. All right, so when I do this, I am going to, the easiest way is to get a common denominator in here first, okay? So simplify that group first before you multiply the other group through. My denominator here is x minus 2 x squared plus 1, right? So I am going to say my denominator is x minus 2 x squared plus 1. My numerator, well, I just need to multiply this one by the x squared plus 1, right? And I need to multiply this one by the x minus 2. All right. So far, so good? Everybody see what I did to get a common denominator? We're simplifying the top. So we have 2x squared minus x squared. So that's going to give us just an x squared. We have 2, and we have a negative and a negative, so plus 2x and plus 2, right? So I just simplified the top. My bottom is x minus 2, x squared plus 1. And then I am going to multiply that by this right here. So multiply that by x minus 2 squared over square root of x squared plus 1. When you do this, by the way, think about our rules for multiplying polynomials. I can cancel something, right? Just like cross-canceling any fraction, I can cancel this with one of those, right? And so I'm going to end up with x minus 2 on top times the x squared plus the 2x plus the 2. And then this is to the first power, and this is to the 1/2 power, right? And they're the same thing, like bases. So 1 plus 1/2 is 3/2. So I end up with just that guy to the 3/2 on the bottom. Don't move. So on the bottom, I end up with just that x squared plus 1 to the 3/2. And that's actually my answer. That's what I would get had I done the quotient rule with the chain rule in there. All right? So it actually does make it easier. The chain and quotient rule leaves a ton of room for error. So it does make it easier in the fact that you're really taking smaller bits of it At the very end, you're getting a common denominator, which you leave a little room for error with your negatives and positives there, but not nearly as much as I feel like a quotient and chain rule ends up being. If I did this one with quotient and chain rule, it'd be a long one. It'd be a really long one because you have to think about the derivative of the square root is going to be a negative exponent. It's going to be, subtract 1, we have x squared plus 1 to the negative 1/2. Like you get a lot of craziness going on in there when you start with that one. So this is just a way to take a larger one and use now what we know about natural logs to expand and make it a little bit easier. Derivative involving an absolute value, you'll see that it doesn't change. Like the derivative, the natural log of an absolute value is still going to be the derivative of that function over that function. And they show the proof of it because you end up with, if you do the derivative of a negative, you can just pull the negative out as a coefficient, right? So you end up, so let's say I had a positive there. Well, if I had a positive, that's just going to be the derivative of that guy over that guy. That's positive, right? Let's say I had a negative. Well, having a negative is like having that function times -1. So I could just say, oh, well, -1 times the derivative over the original derivative, which was negative, over the original function, which was negative. And your negatives will cancel out because it's division. So it ends up just being function, that derivative of the function over the function like the original was. So they gave us a trig one. This is why I want to show you this example because it is a trig one. So trig functions, yes, you do have to remember your derivatives of your trig functions. All right, so derivative of cosine, that is negative sine of x divided by your original function, cosine of x. I would not want you to leave it that way. Why not? Well, because there's a nicer way to write that. Sine over cosine's tangent. So that ends up being the negative tangent of x. All right. There are going to be some of these trig functions that you may want to memorize when you do natural log, but this is an easy one, like really. Derivative of the inside over the original function ends up giving you derivative of a negative tangent of x. Relative extreme, that's your max and mins, right? Max and mins, those happen at critical numbers. So we are going to do this derivative like we would. We are going to take the derivative of that function, which is just 2x plus 2. And we are going to divide by the original function. All right. Where does this equal 0? Well, we're going to set that numerator equal to 0 to figure out where this function is 0. And that's going to happen at x equals -1. Subtract 2, divide by 2. How do I know whether it's a max or a min? Well, I can use first derivative test and plug it in, and I can see what happens before and after. There's no other critical points, so this is the only relative. There may be an asymptote or an undefined point where if we were checking increasing and decreasing, maybe that would be a thing, but we can just do increasing and decreasing for this one interval to see if we have a max or min, right? And so we can go back to stuff. All right, so -1, yes, that's what we're doing. All right, so we are going to say negative infinity to -1, and we are going to say -1 to infinity. We're going to see what's happening here. So let's plug it in. All right, so it goes from decreasing to increasing somehow. So we know this is a relative min. If you want to know the actual point value of that relative min, just plug it in. So my x value is going to be -1. My y value, I go back and plug it in here. So -1 squared is 1, -2 is positive, or -2 is -1, plus 3 is +2. So you end up with natural log of 2. You can leave it like that, or you can estimate it. It doesn't matter. But that's actually going to be the technical relative min if I'm getting an x and y value. So increasing to decreasing would be a max, decreasing to increasing would be a min. You can just apply that test.